So now this is being live streamed to YouTube. Okay. Okay, so now we have this connection between this and YouTube. So maybe some people will be able to watch it on YouTube, and it will be also recorded in the YouTube channel. So it is this is, you know, I don't have much experience with this sort of linking Zoom to YouTube, but it should be working now. Okay. Now we got some more people. Let us wait for a few minutes as people are starting to join. So now we have, you know, external people and students, and okay. So everything seems to be fine on your side. This side, I'm just, you know, people are joining slowly, and it is at the same time being broadcast on YouTube. So we'll see. Okay. So I didn't ask for permission that this is being recorded, Jouko. Is that okay?
Yeah, it is fine, yes.
Okay, and it is also being broadcast through the YouTube channel at the same time. As I said, I don't have much experience in this linking Zoom and YouTube, but it is now being done, and so we will see. Now the advantage is that it gets automatically also recorded on YouTube, and people can watch it at some point
afterwards. But someone can watch it as we speak also.
Yes, of course, yes, and it may be better
in the YouTube, so somebody can go to YouTube and.
Yeah, it is. So I send the announcement also to the Logic group, and people are. So we have people. Let me just tell you. Yeah, I have some students of Logic who are taking for the first time Logic. I have some people who teach Logic in other cities of Colombia, like Rafael Isaacs. I also have, well, there is Juliet, of course, and there are also some people who are joining from different places, or older students also. So I expect quite a few more people, and I don't know how many people are watching on YouTube. Yeah, now people are also joining through YouTube at this point. So
if you are in YouTube, you cannot interact, I guess.
No, you can chat. You can ask a question on the chat. And
I see. But then for those who are in YouTube, the chat doesn't.
Yes, those who are in YouTube right now, the chat is open. And,
but I will not follow the YouTube. Although I could, if I was very kind of competent, I would have another computer with a YouTube open. But I don't think I will.
You got a message from Pedro, who is trying to watch it on YouTube just to see if it works, and he says YouTube has not started broadcasting yet. Okay, so now we have this connection between this and YouTube. So maybe some people will be able to watch it on YouTube, and it will be also recorded on the YouTube channel. I think now it started on YouTube. You know, I don't have much experience with this sort of linking Zoom to YouTube, but so I hear myself now on YouTube. You know, everything is like 30 seconds behind. At some point, I have to stop my. People are starting join. So now we have external people and students. And, okay, we'll see. I propose that we wait for 3-4 more minutes until 12:08, as we are slowly getting a little bit more people, and then I will, just say a few words about today, and very quickly, and introduce you, and we'll.
And you have some program after this also related to, was it a play or movie or?
Yeah, there will be a musical made by some students here. Some of them might be, I don't know if, because they might be worrying about their own presentation.
Yes.
They are logic students who made, 4 of them wrote a script for a musical, and this will be held at the university. So I have to go to university right after this for that. And let's see. I don't have confirmation that more people are watching. Let me just help it just to see, because my lack of experience with this YouTube thing is problematic. Okay, yeah. So YouTube says the streaming is working now. So meeting is now streaming live on YouTube. Also, we have this information here, so it should be now working, hopefully. And I also get something from. Oh, great. Gracias, Darío. Great. Okay. Yeah. There is this time delay. Oh, I see. Okay. Well, let us see if more people join. It's I broadcasted quite a lot in the Logic group here, and I asked people to invite more people, but we will see. Anyway, we have a nice, solid group of students here that should, benefit quite a lot from this. I will now start speaking about the meeting and and the day. So I will start in Spanish very quickly and then switch to English to introduce you. Entonces, bienvenidos a nuestro Día Internacional de Lógica 2022, versión Bogotá. Empezamos el martes pasado ya con algunas actividades. Hubo una charla de Juliet Kennedy, fue una clase abierta para estudiantes de lógica. Hoy tenemos en el programa 3 actividades relacionadas con nuestro grupo de lógica. Está, primero que todo, Jouko Väänänen de la Universidad de Helsinki, Ámsterdam, que nos va a hablar sobre Logic and Games, que va a presentar un poco a Jouko en un minuto. Más adelante tenemos el musical que hemos mencionado, también hecho por 4 estudiantes, el grupo Autómatas de la clase de lógica de la Universidad Nacional. Y por la tarde, a las 6 horas de Bogotá, habrá una conversación con Melissa Gutiérrez de la UNAM, hecha en el canal Física y Feynman de la UNAM. Bueno, espero que disfruten mucho estas interacciones y que si no nos ven aquí, nos vean entonces por YouTube o en algún momento, y si tienen preguntas, puedan interactuar con Jouko. So Jouko Väänänen is a professor at the University of Helsinki, emeritus, and at the University of Amsterdam. And I don't think for us logicians, Jouko needs much presentation because he is one of the great logicians at this moment. Covers different parts of logic, model theory, set theory, infinitary logic, and other areas. But for those of you who don't know Jouko Väänänen, perhaps because you are not a logician, then allow me to say that we are very proud and very happy to have him speak for our group today on this World Logic Day 2022, here linked to the Bogotá Logic Group. Now, why somebody from Helsinki speaking for the Bogotá Logic Group? Well, logic seems to have a lot of symbiosis between different areas and also between different parts of the world. Not so much in the past 2 years, as we know, although maybe the pandemic made this sort of interaction more possible because now we are more used to this sort of a joint seminar. But allow me just to say that the Bogotá Logic Group has enjoyed and benefited enormously from an interaction, hopefully very symbiotic, with the Helsinki Logic Group. Jouko Väänänen is the main figure, I should say, in many ways, in the Helsinki Logic Group. He has many students and many students of students. It's a very beautiful and very lively and intellectually very challenging logic group in the world. So welcome, Jouko, to Bogotá this time. So yes.
Thank you. I can start.
Yes, please.
Yes, thank you for this invitation and for the kind words. Some of them maybe not quite true, but very kind anyway. Yes, and greetings from indeed from Helsinki. So the title is Logic and Games. I will be talking about 3 games throughout this talk, and I will during this this talk I try to give a view about logic. It's really not this logic, that logic, or that area or this area of logic, but logic as a discipline. What is characteristic of it, and what? Well, I'm a mathematician, so I'm sort of maybe biased a little bit in mathematics. Well, here is a quote from a legendary biologist, Thomas Huxley, which gives one view. It has nothing to do with logic, but it's a kind of similar similar view as we take in this talk. The chessboard is the world, the pieces are the phenomena of the universe, the rules of the game are what we call the laws of nature. The player on the other side is hidden from us. This is very much how we work in logic also, and I will now explain a little bit. So there are 3 we're going to talk about 3 games, and they are called evaluation game, model extents game, and repertoire game. So during this talk, I will explain what these games are, but they are connected to some very fundamental concepts in logic, and more in some sense in science and even humanities itself. The first is about truth, because I mean it's a somewhat important concept in science, but here it is an issue in whether a sentence or expression is true in some model. The second game is about consistency, which is like not containing a contradiction, or equivalently having some model. So in the evaluation game, we have both a sentence and a model. In the model existence game, we have only the sentence. There is no model. So it's in that sense it's a related game, but something is missing. So this missing part has to be somehow created during the game. And then the third game, the Erfolg-Freisse game, it is a combination of true and false. But here there is no sentence. There are just two models, and we have to somehow in this game create a sentence. But we have model but no sentence. So this is how they are related. That in this first game we have a model and a sentence, and we argue about truth. In the second we have only the sentence, and in the third we have only model. So this is how they are related. It's really, there is in the background, there is really just one game, but it's somewhat vague concept of game. These three games are completely exact and accurate, technically defined games, but they are like three different views of the same game. And I think that these three games, or the one game which is behind all these, is something essential to logic, something that characterizes logic among sciences and disciplines, and distinguishes, for example, in mathematics, logic from algebra, topology, analysis, and so forth. I mean, there are close connections between logic and algebra. Between logic and topology, logic and analysis, and so forth. But in each case, these disciplines like algebra, topology, analysis, they have their own characteristic, their own thing which distinguishes them from each other, which is sort of really is the heart of the matter. What is it in algebra? Okay, what is it in topology? What is analysis? I won't go into that. Somebody else will talk about those. But in logic, it is these three games. Okay, so now, so here are the three games. They form a triangle, and they, in a sense, support each other in a way which is technically it is like this. So I mean, it looks a bit complicated, and during this talk I will explain what this is. But here are the three games, and then we establish these kind of translations between strategies between these games. So these arrows tie these games together, and that's what we will do in this talk. So I will describe this kind of unity in a sense. Okay, so let's go into business, and the first game number one, is called evaluation game or semantic game, and so there is a model and there is a sentence. You can think of this in many ways. You can during this game, the players are arguing about the truth of phi in this model M. You can think of the model M here. One way to think about it is that it is the world. So, or possible world, or mathematical model, or it could be a database, it could be the computer's present configuration. Now, phi, on the other hand, is a statement in some formal language. For in my case, it is here usually first order logic, but it is something like a statement like every planet has a moon. which either holds or not. Actually, I don't know whether it's true or not, but it is something which we can consider a kind of a scientific problem. Okay, so there are 2 players, 1 and 2, and 1 is like the one who argues for truth. In a sense, it's myself or the scientist, and 2 is the opponent who is challenging the scientist or me. So there are various names that are given to this. Sometimes Hindika used to talk about nature, the 2 is a nature. Nature hits back or challenges you. Or he also talks about demiurge, the creator of the world. Or in the computer science, it's like the environment. Okay, then during this game, we go. So here is the sentence 5. We proceed inside the formula, and at the same time we build an assignment, which means we give values to variables. So there may be some free variables x, y, z. So we give values to them. So here is one assignment. Here is another assignment, and so forth. There are possible assignments. So we create such an assignment during this game. And one way to talk about the games is to talk about positions. To be very particular about what is a position in a game. Like in chess in the beginning, we all know how the pieces are in a certain way, and then during the game the position changes and changes and changes until it is perhaps a checkmate position. So here the starting position is this original sentence that we start with, and then empty assignment because there are no free variables. Okay, so this is evaluation game, but here are the rules of the game. So the rules tell us how to move from positions to new positions. So we start with the position, as I said just a moment ago, with a phi and an empty assignment, and then we proceed according to what this phi is. If phi is a literal, if it's atomic, then the game ends and 2 wins if indeed S satisfies psi in the model M. Because it's atomic, it is something that we don't need to not argue. It is like we just look from a table or from the definition of M, whether this assignment satisfies the literal atomic or negated. Okay, so then comes the more complicated situations. We are in a position where there is a conjunction of 2 formulas. Now, I, player 1, myself, the scientist, claims that this is true. Of course, that we know that what it means. It means that both of them are true. But in the game, it means that the challenger, the nature or demiurge or God, chooses one of them. And if we know that it's true, it doesn't matter which one the nature chooses. So we are sort of all right in both positions. Let's look at then disjunction. That means that I am convinced that one of them is true, at least one of them. So then I should, if I'm so convinced, then I should choose which one is true, and we continue with the one which is true. Universal quantifier, like I said, every planet has a moon. Then the nature chooses a possible counterexample, chooses some A, which means in this case chooses some planet, and then I have to show that it has a moon. And I have no idea what, I mean, I have no control what nature wants to choose. So therefore, we have this quantifier here. Whatever nature chooses, it's going to be true. For me, different challenges extra quantify. If I claim that there is something like there is a moon for this particular planet that was chosen, then I have to produce one. By the way, this notation here means that if you have an assignment and it has some values, then the modified assignment, when you have a or the value of x, means that you change the value of x to a, and otherwise you keep the same. So this is the way to define truth of quantified formulas. Okay, so this is the game, and we use the concept of strategy from Neumann Morgenstern book on games and economic behavior from like almost years ago, I guess. Sure, but anyway, almost. So a strategy is a set of functions which tells what to move at each step, and winning strategy is something which tells you how to win against every play of the opponent. So this is the evaluation game, and now we can define or observe. If we can define the truth in this way, that phi is true in M if 2 has a winning strategy in this game. If I have a winning strategy in this game where nature challenges me all the time, or if I have some other concept of truth, like the Tarski definition of truth, inductive definition of truth, then I can simply prove this as a theorem. I can prove if and only if. It's a nice exercise in inductive definitions to show that the inductive truth is the same as this game theoretic truth. So this is a game theoretical meaning of truth in a model. We can go further and say that the game is the meaning of a sentence phi. There is this distinction whether the meaning is the truth value or whether the meaning is somehow deeper meaning. It's a natural idea. If we want this deeper meaning, then we can say that the meaning of a sentence is this game, rather than the proposition that 2 has a winning strategy. Some people, like Hintikka, whom I mentioned earlier, thought that this game theoretic meaning of truth is better than the inductive definition or Tarski's definition of truth. In my opinion, it is not a question of better, but for some uses of the concept of truth, this is better. For some, it is not so good. But it is the point is that it ties truth to consistency and to equivalence. So it is a very, very useful way to think of truth. I think the origin, according to Hintikka himself, is originally Wittgenstein. In his later philosophy, he gave up the Tractatus theory of truth, and he went into this game theoretic or language game meaning of truth. Leon Henkin in 1961 gave explicitly the game theoretic interpretation of quantifiers in a kind of mathematical sense, and he immediately observed that it can be widely generalized. I will talk about that in a moment. Hintikka made this kind of a part of his philosophy that the game theoretic meaning of truth is in a sense better than the inductive definition. And he also extended it from quantifiers to propositional operations. Now, the nice thing about this game, this evaluation game, the nice thing about this that it reflects very strongly both the monothetic structure of M and the syntactical structure of phi. So, for example, if M is the product or a sum or reduced product, some or other I mean, if it has internal structure, so like in a sum, disjoint sum, two models, they are put together like this. So if you have M1 and M2, then the sum is this. While in the product you make the usual way, and then the reduced products and so forth. If you have strategies in these models, for these models, you can get a strategy for the sum. If you have a strategies for the components, you can have for the product, and for the same for the reduced product. And Febberman wrote a very influential paper in the 70s in which he showed how to translate these individual strategies, how to combine them into one strategy in the product sum and reduced product. So on the other hand, if you look at the structure, internal structure of phi, I mean, it's a first order formula, so it can be quantifier free, it can be universal, existential, universal, existential, etc. And they totally immediately they reflect in the game, so that the game is somewhat different. If we know that phi is quantifier free, the game is quite different. I mean, simpler. If we know phi is universal, the game is simpler, and so forth. So the game is like totally married with the structural model and the structure of the formula. And the beauty of this game theoretic semantics is that you can do this for other logics than first order logic. So we can add new logical operations such as infinite conjunctions and disjunctions, then as quantifiers or higher order quantifiers. Let's see if yes, here is for higher order for infinitary logic. So we have this L infinity omega here, and so then if we are in a position where the formula is infinite arbitrary conjunction, then it just means that okay, here is Abelard, it should be 1, and here is LR should be 2. Abelard choose nature chooses 1, chooses an index, and then the next position is that formula. And if it is a disjunction, then I choose, or player 2 chooses the index. Here is an interesting case of a generalized quantifier Q1 that, for example, Javier Caicedo from Bogotá is a pioneer in studying. If we are in a position where the logical operation is Q1, which means there are uncountably many X, or or you could also say that there are many X. Then player 2 first chooses an uncountable or a large set X, and after that 1 chooses an element from the set, and the next position is here. So here the action of moves of the players in this position are a bit more complicated. So first, I choose an uncountable set, and then nature chooses an element from that set. But that works perfectly, and that gives exactly the same truth definition as the original Mostowski definition. Maybe well, I say quickly that one can also extend this to so-called theme semantics. A theme is a set of assignments. Like here you can see a lot of assignments. It's not just one assignment, but there are like 1, 2, 3, 4, 5, 6 assignments together. And you can define this game theoretic semantics for this situation in which there are many simultaneous parallel assignments. And then it just means that the position is a pair of a formula and a theme. So here is an example of a theme. So here are the variables, like this could be x, y, z, u, but in computer science people not use these kind of variables, but names like
Jouko.
Like this. Yes.
Are you writing something? Because I don't see any writing on your screen, but you seem to be referring to you're writing something now.
Yes. So let's see. Yes, I can see now that. Okay. Now you can see.
Okay. Thanks.
Yeah. Yes. Tell me when it freezes. But okay. So and here are the assignments: first assignment, second, and the third. And so this is like a computer science example of a theme, but of course mathematically it is just a set of assignments. So the point of this is that one can define this game theoretic semantics for new atomic formulas like this dependence atom, the meaning of which is that y is completely determined by x. This goes beyond, of course, first order logic, but it is useful in social choice theory and quantum mechanics, where we typically don't have just single observations, but many observations and we look at the correlations or here like concepts of majority. Okay, so now let's go to the second game. So this is model existence game. Now we have a sentence. We have no model, just a sentence. And now we play the game in which I claim, or player one claims. Sorry, player two claims that that the sentence is consistent, or that it has a model, that it doesn't contain contradiction. So a position is a finite set of pairs psi s, where psi is a formula and s an assignment into C, and C is just a countable set of constants. So we fix that in advance. It's just a set of constants with no structure, internal structure. During the game, we create some structure into C, and we start with a single pair phi empty. During this game, at every point, player one, which is the nature, decides which pair we act on, and the next position comes according to these rules. So so here is the first rule. If this set, finite set S, contains a conjunction, then player one can pick it on the table, so to speak, and then continue with either conjunct. If the set contains a disjunction, then I can continue with one of them. I can decide which one we continue with. So, okay, if it is a universally quantified, then again, nature chooses some constant, and we continue with the idea that x has value, that constant has value. And if it is an extensively quantified formula, then I choose the constant. And the whole point here is that if at some point we have a contradiction, that we have both psi and not psi in the set S, then one wins, because one is kind of looking for contradiction, and two, myself, claims that that there is no contradiction. So instead of in the previous game, there was one model and a sentence, and so it was clear all the time, in a sense, what to do. If it is true there, then I follow the truth. But if it is false, then nature follows the falsehood. Here, this set S somehow estimates the possibilities for truth, in which way things can perhaps be. And so if it is possible, for example, here, if it is possible that conjunction is true, then of course it is possible that both of them are. I mean, for both of them, it is possible that it's true. If it is possible that disjunction is true, then I just look at that possibility, and then I can see that I can say that this is possible or this is possible, and so forth. Okay, so this is the model existence game. In the connection to the evaluation game should be clear. There is some kind of atomic case, and then there is the conjunction. One chooses disjunction, two chooses universal quantifier, one chooses extensor quantifier, two chooses. Here is the same conjunction. One chooses disjunction, two decides universal quantifier, one chooses extensor quantifier, two chooses. And the kind of the easy case here is that if we already have a model and a sentence and two, so I already know that phi is true there, then of course I can also win the model extents game, because I use this particular model that I have. So I play everything according to what is true in M. So technically what happens is that first I have to take a countable elementary submodel of M by closing under the strategy, and so that gives a club of countable subsets under which it is closed, and then I interpret the constant C in one of those, that club, and then I play according to what is true in that countable submodel. The winning strategy tau still works, and then I can copy that. So it is copycat strategy. So this is like the in a sense somewhat trivial direction. This is the less trivial direction, that if in the model existence game player 2, myself, has a winning strategy, then I can use that strategy to create a model and a strategy in the evaluation game. This was introduced by Beth in the 50s already. Did I say yes? So here I forgot to say that this model extents game was introduced by Beth at the same time Hintikka, and then it was like developed and made into a very smooth form by Raymond Smullyan, and it was extended to infinitary logic and used in a very extensive way by Michael McKay. So this is like a short history of that. Oh, sorry, I went too far. Here, Beth, who used Gerhard Gensen's natural deduction as an example, he used this method to prove a kind of a completeness theorem in which he thought was not as theoretical as Gödel's completeness theorem. Also, Hintikka was motivated by thinking that this is more effective. In technical terms, it's not more effective. It's all delta 0 2. But intuitively or philosophically, maybe there is some benefit in this kind of model construction. Especially, it didn't seem to use axiom choice in the same sense as, for example, Henkin's completeness theorem. Mind you, Gödel did not use very much axiom choice either. Okay, so here is now, I said in the beginning that we create some translations between these. Oops, there is some mess here. So what we have done now is establish these connections between from truth, how from truth we get consistency. That's kind of the trivial, and then how consistency we can get a model and truth. Now some remarks about this. I mean, this is a game, so we think of game usually that, oh, I should win this game, and if I don't win, then it's not so interesting. But these games are determined. So one of the players has a winning strategy. Suppose I don't have a winning strategy, then by determinacy, I mean Gale-Stewart theorem, player 1, nature has a winning strategy. And there's some interesting things one can say about this winning strategy of player 1. In fact, this was the motivation of Beth, and he thought of the winning strategy of player 1 as a Beth tableau, which became then a method which is used even today, especially in computer science. So you form the tree of all positions when one plays his winning strategy, and we stop playing as soon as one has won. So it is like all possible challenges of the to the consistency, and if they all these challenges lead to one winning, it means that it cannot have a model. every branch of this tree is finite because player one has a winning strategy, so every play that is played, he wins at some point. Now we can make this tree finite by being a little bit more careful how the game is defined, and then that means that we can consider the tree as a proof. And in fact, this is what Jensen did in natural deduction. Proofs are kind of trees. So we get the proof of the negation. And so this winning strategy of 1 gives us a proof of the negation, and winning strategy of 2 gives a model for the sentence. So in this sense, this one game somehow codes a bridge between proof theory and model theory. Proof theory is very much about Jensen systems and their properties. Model theory, the starting point of model theory is construction of models. And yes, so this is essentially a form of compactness theorem, this model existence theorem. But it is more delicate than the use of compactness. For example, it gives very easy proofs of interpolation theorems. So therefore, I talk about a bridge between proof theory and model theory here. If we look at winning strategies of 2, I mean, winning strategy of 1, I said, was a proof, a form of a proof. Winning strategy of 2 can be thought of as a so-called consistency property. And this is what I said. Smalian and Mackay made very efficient use of this, the 60s in infinite logic, and still today it is very useful in model theory. It is. I'm not going to say what the consistency property is, but it is essentially the same as a winning strategy of 2 in the model existence game. By the way, there's a recent result of set theory due to Asperot and Schindler, which they show that Matis maximum plus implies Woodin's star axiom, and the proof uses consistency property in set theory. Yeah, it's a consistency property for propositional logic, which is used there. So it is very much, this concept is very much used nowadays, and it's very useful. Okay, so now let's go to the third game. Oops. The Ehrenfeucht-Rice game. Now here, we don't have any sentence to start with. We have just a model, 2 models, and we are looking for a sentence. But we can formulate this. It's very useful to think about this as a question. Are these 2 models isomorphic? As you know, if they are isomorphic, they satisfy the same sentences. So if we can find a sentence which is true in one but not in the other, then they certainly are not isomorphic. But maybe they are very close to being isomorphic, but not exactly isomorphic. Okay, in this game, player 2, myself, claims that they are isomorphic without actually knowing or having an isomorphism, and player 1, the nature, has doubts. So a position in this game is a set of pairs. So let's look at the picture. So here are the 2 models, M and N, and here are the points A, N, and B, N. And during the game, we create this kind of connection between these elements. And the idea is that the elements here, these satisfy the same atomic formulas in M, for example, the same equations as the corresponding elements in N. So a position is as in this picture, this kind of elements being coupled with each other, and we move as in all of these games. We move from position to position. So let's see how the next position is decided. In this case, the next position from S is obtained so that nature chooses an element from one model, and then I choose corresponding element in the other model, or vice versa. Nature chooses in the N, model N, and I choose them in N. So in that way, so like here, the next move is player one chooses, for example, here A4, and then I choose here B4, and then that means that we generate this move. So it's very simple game. We have two models, and we just play like this as long as the game lasts. And the player one wins if on the left hand side some literal is satisfied in M, but on the right hand side the corresponding sequence does not satisfy the literal. I mean, the interesting question is how long games can I win if it is known that they are not isomorphic. I may still be able to play like 5 moves against any challenge, but in 6 moves I would lose. So pairs of models are classified in this way, how similar they are. It's particularly interesting, well, particularly hard for games which last for infinity, transfinitely many moves. So there are many reasons why one could think of this as a logician's version of isomorphism. Isomorphism because it sort of imitates isomorphism between them. And if they were isomorphic, then of course two has a winning strategy. And a logician's view, because as it turns out, having a winning strategy in this game is absolute in set theory, while the real isomorphism is not absolute. So you can have 2 models which are not isomorphic, but you add a Cohen real and they suddenly become isomorphic. So it's not an isomorphism is not absolute in set theory, but this is. And there is a certain sense which I will describe why you can actually identify this game with formulas. As I said in the beginning, there is no formula, but well, you will see. Okay, so the screen is frozen. Okay, let's see.
So what we see is a logician's version of isomorphism.
Yeah, yes, but I already moved forward.
Okay.
I think it is. I think we just have to wait a moment. Let's see.
Strange. Or maybe close it and open again the presentation. I don't know. Yeah, wait, don't.
Okay.
Share.
So I will stop sharing, and then we hope that. Okay. let's see. Yes. No.
Okay, now strategy of two implies elementary.
Yeah. Yes. Yeah. So if in this game, which is again it's a determined game, so one of the players has a winning strategy. If player 2 has a winning strategy, then this thing maybe I show as a picture first. So here is the winning strategy of player 2. What the theorem says is that if we have any sentence of even an infinitary sentence here, which is true on this side, then we can transfer the truth onto the other side. So true from here is transferred into the truth on the other side. So so if we have a strategy, let's say winning strategy sigma of myself, player 2, in this. So just as I have here, I have a sigma. Yeah. From that winning strategy and the strategy in the equivalence. So from this and this, we can compute very explicitly a strategy for phi in this model N. So the strategy tau, in a sense, transfers truth of any sentence of certain quantifier rank to any model where any other model where this tau is a winning strategy. So this is the point of this. This was proved by, let's say, Ehrenfreud in 1961. So suppose phi is an infinitely omega sentence of quantifier rank at most m. Every strategy tau of 2 in the Ehrenfreud-Price game of length m, and every strategy sigma of 2 in the model existence game for m and phi. Determine a strategy of 2 in the model existence game for phi in n. This is in elementary model theory. This is called elementary equivalence. That if 2 has a winning strategy in the game of length m, then the models are elementary equivalent up to quantifier rank m. So this again is a somewhat trivial fact, not particularly deep fact, but it is quite useful. Namely, again, there is a tight connection between these strategies, sigma and tau, and the composition strategy, which is which goes deep into the structure of M. For example, if we know that phi is extensile, universal, or positive, we can modify the Ehrenfreud game accordingly by stipulating that one only moves in M, only moves in N, or has to win by finding an atomic rather than literal relation which shows in M but not in N. Also, the strategies reflect structural properties of M and N. And again, there is this work by Pfefferman, and then there are more recent results in finite models by, for example, Grohe, that if we know winning strategies in the component games, then we can build winning strategies for 2 in products and sums and such. So with this method, certain things which in logic just become combination of strategies and building of strategies, especially winning strategies in this kind of back and forth games. because once we have the strategy, then we know, because of this theorem of Erefort, that certain sentences are preserved in these models. This is particularly useful for showing that some property cannot be expressed in first order logic, because you get two models which are where player 2 has a winning strategy. One has the property and the other one doesn't. So there cannot be a sentence which separates them. You can show, for example, that well-foundedness, well-ordering cannot be expressed in infinite logic by for every alpha you can find a well-ordered model and a non-well-ordered model where player 2 still has a winning strategy in this game. Okay, so this is the trivial direction. The less trivial direction is this, that if we are given, if we fix a model.
The slide is still, there is a
Okay.
tight.
Okay. Okay, now.
Oh, yeah, no.
We are given a model, and now comes the moment when from the game we extract a sentence. There is a sentence file which we can explicitly write down, such that for any other model n and any strategy of player 1, the bad guy, the one who is challenging us, in every model where the bad guy has a winning strategy, there is a strategy for me in the model M and a winning strategy for the bad guy in the model N. So we can translate the difference that in one model, that the difference of the models, which is witnessed by player 1 having a winning strategy in the Erefort twice again, we can witness that by a sentence. We can translate this game theoretic fact into syntax. So from kind of a mathematical game theoretic fact, we can pull off this syntactic formula, which tells the difference. So if player 1 has a winning strategy, so remember that it means that there must be some difference between those, like that this has a triangle, but this does not have a triangle. If there is such, then we can write a sentence phi, for example, a sentence which says that there is a triangle, which is true here, but false here, because player 1 has a winning strategy. So this is a way in which this kind of mathematical game corresponds to purely logical syntax. We can again make many observations about connections between the models and between the strategy here, tau, which is the winning strategy of player 1. If we assume that the bad guy only plays on the left-hand side, then we can make phi existential. If the bad guy only plays on the right-hand side, we can make phi universal, and we can also make it positive under a further assumption. We can write the CF games also for infinitary logics and generalized quantifiers. Javier Caicedo wrote important paper on this in the 80s, and higher order logic, and we can do this also for modal logic. And we can do this for teams and even for propositional logic, but I won't go into that. And we can use these teams to do this for L omega 1 omega, and we can modify the game into a concept of so-called delayed game, which gives an interesting intermediate infinitary game that I'm studying with Andres Villaveses at the moment. We have just finished the paper on that. So summary. I talked to you about 3 games, and I claim that they incorporate everything important in logic.
Let us look at the slide transition somehow. We still had many useful observations can be made. But,
okay. So I go a little back. Yes. So what is?
So we are at the remarks.
Yes.
Session.
Okay. So I will make it quick by making this again. Taking again the connection. It was okay.
Yeah, looks like yeah, right. Okay, so we have.
Yes. Okay, so this is what you saw, and here is we can do this for infinite logics and quantifiers as Javier did in the 80s for model logic, and we can do it for teams and also for this delayed game, which gives an interesting Lindstrom theorem, something we are doing with Andres. Okay. And here in particular comes the question, what is the connection between syntax and the game? And here it's an interesting question. What is the difference between having a syntax and not having a syntax? Okay, so summary. So I try to incorporate here all the important concepts: truth, consistency, formula, proof, structure, and even the human user, because it's a game. After all, we think of it as game played by humans, even if it's a mathematical game. And what else is important in logic if it's not truth, consistency, proof, and structure? Also, it is in a sense uniform approach, a coherent uniform approach to syntax and semantics, to model theory and proof theory. Now, what is one interesting thing is that the EF game is oblivious to whether the models are finite or infinite. So it is just as useful in finite models as infinite models, and it is in theoretical computer science. It is used all the time in to study properties of finite models, which tend to be even more complicated than the properties of infinite models. And I think that there is a lot of potential for further study the interaction. So how effective are these translations that I have described here? Translations of strategies. I mean, are they somehow functorial translations? And there is some research on this by recently by Johan van Tentem and also by Anos Davar and Samson Abramsky, and I and myself a little bit also. So I think it is a fruitful topic and fruitful approach. And here is my final picture. Thank you very much.
Thank you very much, Jouko. Thank you. It was, thanks for this wonderful view of these 3, games that somehow allow so many bridges between so many different things. Let us, if there are any questions from people here, please, if you have questions, this is the time. We have some time for questions. I do have a question. Let me try to formulate it, because in this transition from finite to infinite, so you have so the game approach, works for finite models, for infinite models. But what about the asymptotic properties of finite models? Can they be somehow reflected in the games somehow? Asymptotic, as there are finite
Yes.
rows?
Yes. Yes, it's a very important question, and good question. There are these the so-called 0-1 laws, which hold, for example, for first logic, but also for L infinity omega. If we make the following adjustment, that we decide that there is natural number n, so that the formula uses only n variables, free or bound. So only n different variables are used, whether it's free or bound. So this has arisen in computer science. It's related to recursion. It was introduced by Immermann and Moskovakis in the 80s or 70s, 80s. And there is a natural game for that, which means the so-called Pebble game, that you, which means that you can only, you put pebbles on elements, like here, that they are pebbles, and then you have in the beginning, you have a certain number of pebbles. And when you run out of pebbles, you have to start taking the used pebbles away. So you can only use this 1, 2, 3, 4, 5, 6, 7 pebbles. And that corresponds exactly to equivalence with respect to 7 variable formulas, whether they are finite or infinite. So, and the first proof of Ronald Fagin in the 70s of the 0-1 law for first logic actually used infinite models. So you take a he took the recursively saturated infinite models. They are and their isomorphism under certain condition. So the connection between infinite models and finite models is very natural in this in this context.
Yeah. I was thinking of more. Now, I have another more technical question, but not for now. So, thank you very much. There are no more questions by anyone. No questions by. Okay. So, thank you very much, Jouko, and
thank you.
Thank you. So, continue. By the way, this is now being broadcast. So there are some people here, and there are some people also in the YouTube channel. They're watching it. There is a little bit of delay between the two, but since this, what happens with these things is that more people watch that in a kind of delayed form in YouTube, and it is more effective than Zoom recording for some strange reason that I don't understand. The Zoom seems to attract more, viewers. The problem is you don't know who they are, because they might appear. I mean, some of them, of course, might write at some point with some questions on this, but we will see. So I will send the information on the